Hi, I'm Dane Quinn from the University of Akron, and this is another example modeling multi-degree of freedom systems, and this is for fundamentals of mechanical vibration. So here's the problem we're going to look at today. We have a bar of length L, and it's pinned a third of the way down at O. Notice the mass center is in the middle of the bar. It's uniform, denoted by G. On the left side of the bar, we have a spring and damper in parallel, connected to the ground, and then on the right side we have a spring that then supports a block of mass m. So when we solve this problem, the first thing we'll do is think about the system, and in particular we'll identify the objects, and there are two of them, the bar and the block, as well as the forces that act on those objects. So here let's go and draw those two objects. The first one we'll draw is the bar. So there it is. And then we'll draw the block as the second object. And then let's identify the forces that act on these objects. So at O, we have a reaction force. I don't really know anything about it, right? So I'll just kind of put it at arbitrary angle. Right? So we'll call that R. And then we have the force on the left side due to the spring and the damper. And we'll call that force T. Then we have a force on the right side from this spring. Right, so we'll say that is down, and then this force acting on the block we'll define as Fs. So it's the spring force, which means that this force will represent as minus Fs. Again, we're neglecting gravity in this system because we're measuring from static equilibrium. So the effect of gravity would balance out, the initial stretch, for example, in this spring. And then the effect of gravity on this block will be balanced out by the static equilibrium stretch in this spring. So again, when measuring from static equilibrium, if the bar is horizontal, we can neglect the effects of gravity. Right? So here, T is the spring damper force on the left. This force will be defined by constitutive relationships between the force and the displacement across the spring, as well as the velocity across that damper. R is the reaction force acting at the pin. It's a constraint force. And then finally, Fs is the spring force between the end of the bar here and the mass. So again, that will also be defined by a constitutive law. So now the next thing we do is identify coordinates and directions. The directions we'll use are I and J, horizontal and vertical. So let's look at the motion first. This bar rotates, right? So it makes sense to define the angle of rotation as one coordinate. Now this block moves, so we will define the displacement of that block with respect to the ground as x. Notice that this is a 2-degree of freedom system because we need to know where the bar is, and that can be done with the angle theta, and then we need to know where the block is, and that can be specified by the displacement x. However, we're going to use more coordinates than that because the spring force, for example, is dependent on the stretch in the spring. So here I can define the stretch in the spring as z, and then we can also identify the absolute position of the upper point as w. Then looking over on the left, the stretch in the spring we can define with y. and then y dot is the velocity across this damper. Right, so these forces are going to be directly dependent on y. This force will be directly dependent on z, and then x, z, theta, y, w are all related. So notice that I have 1, 2, 3, 4, 5 coordinates. And again, those are x, theta, y, z, and w. But I have a 2-degree of freedom system. So that means that I need constraint equations, or I have constraint equations that link 3 of these coordinates to 2 others. So in particular, let's look at y first. Y and theta are related. Right? So here, y is L over 3. And I'll remind you that this distance was L over 3 times theta. So if theta is positive, y is positive. And here positive y indicates that the spring stretches, right, or the left point moves down. I can also determine a similar relationship between w and theta. Right? So here w is 2L over 3 times theta. Right? And once again, in terms of the length of the bar, this distance is 2L over 3. So then finally, x, z, and w are related. So the displacement at the top, at the end of the bar, w, is equal to the displacement of the block plus z. So now I have 3 constraint equations for 5 coordinates and a 2-degree freedom system. So at this point in our procedure, we will identify the kinematics. So essentially, that implies looking at the acceleration of the block, right? Because the block moves up and down, so we'll need to find the acceleration. And the easiest coordinate to do that is x, right? So the acceleration of the block is x double dot in the j direction. Likewise, the bar rotates, right? So the angular acceleration of the bar, and actually let's call this point A. So the angular acceleration of the bar is theta double dot in the k direction. Notice that I'm using vectors throughout this, right? So the acceleration I represent is x double dot in the j direction. And the angular acceleration is theta double dot in the k direction. It's not just x double dot, and it's not just theta double dot, but it's a vector. So magnitude and direction are both important. But in terms of these coordinates, right, this is the easiest way to represent the kinematics of the system. So now our next step is to define the free body diagram. And just for reference, I have included the coordinates that we defined on the previous slide. But now we want to write these forces, and remember this force was R, this force was T, this force was Fs, and this force is actually minus Fs, according to our previous definitions. So now let's just go through the forces one by one and write them in terms of the coordinates if they are given by constitutive relationships, or just identify unknowns. So the reaction force here, I don't know anything at all about it. So I'll just say that it's Rx in the I direction plus Ry in the j direction. Now, this spring force over on the right side is related to the stretch in the spring, right? So here, Fs is equal to k times z in the j direction. So if z is positive, then the force acting on the block is directed upward. All right, so I get k times z in the j direction, which means that the force acting on the bar is minus k times z in the j direction. Now finally, the tension, or the force acting on the left, is a combination of the force in the spring and the force in the damper. So here, if y is positive, right, so that the left side moves down, then this force is up due to the spring, and it's k times y in the j direction. Likewise, if y dot is positive, then the force from the damper adds to that. Again, they're in parallel, and that's b times y dot in the j direction. So t here can be written as ky plus b y dot in the j direction. So now we have a complete description of the forces that act on this system. On the previous slide I have the kinematics, and now I'm ready to apply the equations of motion. Right, so for linearized motion, and that implies small angles, then we have sine of theta, which this is my shorthand, s theta, again it means sine of theta, is approximately theta, and cosine of theta, again that's my shorthand for cosine of theta, is approximately 1. Now when we apply momentum balance, we'll apply angular momentum balance on this bar about 0.0 since it's fixed in the ground. So we need the moment of inertia about 0.0. And for that we'll use the parallel axis theorem. Right? So that says that I0 is the moment of inertia about g, right? So this point is g, plus the mass times the distance between those two things, those 2 points, g and o, which is L over 6. The moment of inertia of a bar about the center is ml squared over 12. The second term is ml squared over 36. Right? So a little bit of algebra, ml squared over 9. Right, so now I can apply angular momentum balance. And we want to take that about 0.0. 0.0 is fixed in the ground, so that's a perfectly valid place to take angular momentum balance about. And moreover, it eliminates this reaction force, which is unknown, and that's good. If I take angular momentum balance about g, which I could also do, I would still have moments due to the reaction force. And then I'd also have to go and apply linear momentum balance on the block. Right? But taking angular momentum balance directly eliminates those reaction forces. I'll remind you that moments are defined as r cross f, where r is the position vector from the point that you're taking the moment about to the point of application of the force. And so here, some of the moments about 0.0, well, I'm going to have two forces that produce moments. One is this force on the left, so this is going to produce a moment in the negative k direction, right? So that's going to be minus ky plus by dot. And then the moment arm is L over 3, and that's in the k direction. This force produces likewise a negative moment, so that's minus k times z, and the moment arm is 2L over 3 times k. If these confuse you at all, go back, maybe pause the video, and work out this cross product. For this force, r here would be minus L over 3 in the I direction. Right, so I cross j is equal to k, but we have a minus L over 3. And then for this force, it would actually be 2L over 3 I cross minus kz in the j direction. And again, this is what we get for that. So that's going to be equal to moment of inertia, which we said was ml squared over 9, theta double dot in the k direction. Right, so again, that's simply I0 alpha of the bar. Once again, our laws of mechanics are some of the moments equals I alpha. Then, looking at, let's do linear momentum balance over here. On the block, so looking at the block, we have the sum of the forces. Well, there's only one force, k times z in the j direction, and that's going to be m x double dot. Remember our kinematics. Let's see, where was that? Here. The acceleration of the block A is x double dot in the j direction. And again, mass times acceleration of A. So the laws of mechanics are sum of the forces equals mass times acceleration. So we can pull off these two equations, and we end up with the following. Minus kz times 2L over 3 minus ky plus by dot times L over 3 equals ml squared over 9 theta double dot, and equals ml squared over 9 theta double dot, and kz equals mx double dot. So if you'll note, I have two equations, but I have actually 1, 2, 3, 4 coordinates. All right, so my coordinates are z, y, and y dot, theta double dot, and what color have I not used? Blue. X double dot. So now I have 4 coordinates and 2 equations, but remember I also have 3 constraint equations. So my constraint equations were y equals L over 3 times theta. I have w equals 2L over 3 times theta, and w is equal to x plus z. And so now I have 1, 2, 3, 4, 5 equations and 5 unknowns, including this new unknown w that's here in the constraint terms. So here I've rewritten those equations just in a nice clean form, and now we can choose any 2 set of independent coordinates to find the equations of motion. So let's choose y and z. Essentially, this is the stretch in the left spring and the stretch in the right spring. So we want to write theta, w, and x in terms of y and z only, because after all, we need 2 independent coordinates. So we'll just look at these constraint equations and then go and solve for theta to be 3 over L times y, right? So I just solved this for theta. Looking at w, we see that w is 2 times L theta over 3, which L theta over 3 is equal to y, and we find that w is just twice y. And finally, x is equal to w minus z, or 2y minus z. So using these 3 relationships, we can substitute those into the equations that we obtained from momentum balance and find that ml squared over 9 times theta double dot, right? But remember, theta double dot is 3 over L, and in this case it's y double dot, right? If I want to find theta double dot, I'll take the derivative of this equation twice, and so this becomes theta double dot, this becomes y double dot. plus now 2kl over 3. Right, so I'm going to look at this term next, times z, and then plus L over 3 times ky plus by dot equals 0. And the second equation becomes m times x double dot, so that's 2y double dot minus z double dot minus k times z equals 0. So I just kind of brought everything to one side. And I can simplify this a little bit. And ultimately, I can write the equations of motion in the following form. Notice that this 3 and cancels out with, well, at least 3 of those 9s. So we get m over 3 y double dot. I'm actually going to factor out an L from every single one of these terms, plus b over 3 times y dot plus k over 3 times y plus, now we have 2k over 3 times z equals 0. So that's this first equation. And then the second equation can be written as 2m y double dot minus m z double dot minus k times z equals 0. So now these are our equations of motion, written in terms of y and z. Notice that I can write this in matrix form. Right, so the mass matrix would be m over 3, and then there's no z double dot term here, so I would get 0 in that element. So y double dot, z double dot. Notice that now we have a damping matrix, and that's going to be b over 3 times y dot. There's no damping term associated with z dot, so we have a 0 in that element. And then finally the stiffness matrix is k over 3 and 2k over 3 y and z equals 0. My second term, or my second equation, we would have 2m times y double dot, and then minus m times z double dot. There's no damping terms at all, right? So both of those are 0. For the stiffness, there's no k, or there's no y term, and then we have minus kz equals 0. So here, this would be the mass matrix, this would be the damping matrix, and this would be the stiffness matrix. So, for this system, we're able to apply the equations for momentum balance, identify the constraints, free body diagram, and then finally we're able to reduce this to two equations, one here and one here, in terms of two independent coordinates. And in this case we've chosen y and z. If we chose different coordinates, we would get different equations, but it would still model the resulting behavior of the system. So that's it. Thank you very much, and I will talk to you again. Bye. So now, given these three coordinate relations, we can take them, substitute into this equation, and find that ml squared over 9 times, well, what would be... Hey! Hush! No! What?